It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today we are going to talk about the twin paradox and black holes, specifically how time is affected by black holes. Before we get into that, let's do an example of time dilation. We're going to start with a person in a spaceship. That's the Winnebago from Spaceballs. And inside the spaceship, we'll say that they have a pendulum that's free to swing back and forth. And this spaceship, we'll say, is traveling to the right with a velocity of 0.910 times the speed of light. There's a person inside the spaceship, and they're going to time one period of the pendulum, so the time for the period to go back and forth. When they do that, they get a time of 8 seconds. Because the person inside the spaceship is moving with the clock, relative to each other they are at rest. So that's the proper time, is 8 seconds. Back on Earth, we have somebody with a clock, and they could somehow see this pendulum swinging back and forth. And we want to know what time do they get on their clock or stopwatch. As we saw from the previous video with trains, the person on Earth is going to see time slow down for the person inside the spaceship. So what that means is that the time for one pendulum swing, or one period, is going to take longer on their clock. So the time for it to go back and forth is going to take a longer time, which means they're going to have time dilation. Time is going to get stretched out, and they should get a larger number. So we're going to measure the dilated time, which we're calling delta t, for the person on Earth. The formula we have is delta t is equal to delta t proper. That's the time measured by the person stationary relative to the clock, in this case 8 seconds, all over the square root of 1 minus v squared over c squared. So in this case, all we have to do is plug and chug. So delta t is 8 seconds, all over the square root of 1 minus 0.910 c quantity squared, all over c squared. In this case, the c's cancel out, so it's just 1 minus 0.910 squared. When we plug this in our calculators, we get a time of 19.3 seconds. So what that means is the person on the spaceship that's stationary with the clock, appears to be stationary with the clock, gets a time of 8 seconds. The person that's observing it from Earth, because the spaceship is moving away from them, time is going to slow down, which means it's going to take longer for the pendulum to swing back and forth. In this case, it took 19.3 seconds. So now, let's look at the twin paradox. We're going to have a similar situation. We'll have a person a twin standing on Earth. And the twin tells their other twin, we'll call the twin on Earth Al. They tell their other twin in the spaceship to travel at 0.5 times the speed of light. So 0.5 c. And they want them to travel a distance of 7.5 light years away from them. One light year is the distance light travels in 1 year. So they're going to travel 7.5 light years out. And then they also want to return back to Earth to say hi to their twin. So that's another 7.5 light years. If we do the math, we could look at Al on Earth and his twin. Let's just call Joe. And his twin on the spaceship. So if we do simple math, we could do the velocity is distance over time. And what we want to do is calculate the time that Al feels on Earth as Joe went 7.5 light years away and 7.5 light years back. So we get time is equal to the distance over the speed of light, over the speed of the spaceship. Time, we get 15 light years, that's the total distance, divided by 0.5 c. And if we plug and chug, we get the time to be 30 years. So that's how much Al has aged when Joe went down and back, 30 years. From Al's perspective, that's his proper time. The time's just ticking normally. But as we saw from the picture above, this delta t is going to be the dilated time. So even though it's Al's normal time, we're going to call it the dilated time. What we want to do is look at Joe and see how much Joe has aged as he went down to some star, galaxy, to some star or planet, and back. So Joe also has a clock on his spaceship that's ticking normally. So we want to calculate Joe's proper time. How much did his clock say he aged? So our goal is to find T prop from Joe's perspective. Why don't we make a chart for Joe? So from Joe's perspective, we're finding his proper time. And we know that Al's clock ticked for 30 years. So the dilated time is going to be 30 years. And we know that Joe is traveling at 0.5 times the speed of light. So let's start with a formula for time dilation. That's delta t equals the proper time for Joe's perspective over the square root of 1 minus v squared over c squared. In this case, we're solving for the proper time for Joe, so we'll isolate that first. So t prop will be the dilated time times the square root of 1 minus v squared over c squared. And we'll plug and chug, so we get 30 years times the square root of 1 minus 0.5c quantity squared over c squared. We plug and chug and we get approximately 26 years. What that means is that Joe felt like it only took him 26 years to go down and back, while his twin, it felt like it took 30 years on Earth. So when Joe comes back, he's going to be 4 years younger than Al. Now that sounds like quite the paradox, But this is acceptable. We'll get to reasons why it's weird in a second. But this is not the paradox, the fact that Joe is 4 years younger than Al. Where the paradox arises from, or part of the paradox, is that we can look at Joe's perspective and say that Joe is stationary in his spaceship, and that Earth is moving away from him at 0.5 times the speed of light, and the Earth is going to the left 7.5 light years, and then back 7.5 light years. Which means in this scenario, for Joe, the time he measures, it took 30 years. And then for Al on Earth, he's going to feel the proper time. And for Al, based on our math, he's only going to age 26 years. So the dilemma or the paradox arises when we have two situations at the same time. We could say that when Joe returns to Earth from the left side, he could either be 26 years older, or in the second scenario on the right side, he can also be 30 years older. So this is where the paradox arises, that yes, it is okay for Joe to age differently than Al, but there can't be two options for Joe's age. He can't be both 26 years older and 30 years older. Now, where the dilemma arises is, let's look at the picture on the left. As Joe is flying away to 7.5 light years, he eventually has to turn around. And that turnaround, when we change our direction, that causes an acceleration. And when an object is accelerating, the rules of special relativity no longer apply, and we have to look at general relativity for an accelerating system. What happens is during this period of acceleration, Joe's clock is going to slow down or tick slower, which means from his perspective, Al's clock is going to tick faster. And what happens is the time that Joe experiences is going to be a total time of 26 years. No matter if it's Joe that's accelerating, or Joe that's moving to the right, or if the Earth is moving to the left. So during this period of acceleration, no matter what happens, Joe is still going to end up being aging 26 years, which means that he's 4 years younger than his twin on Earth. We also saw that from the previous video, when you're in elevators, it's hard to know, if it's impossible to distinguish if an elevator is accelerating upwards at a zero gravitational field, or if an elevator is just sitting still in a strong gravitational field. Both of these are the same situations. So it's part of the equivalence principle. The person accelerating upwards in zero gravity will experience the same force as a person standing still in an elevator in a stronger gravitational field. Which means that if Joe is accelerating, like the person accelerating upwards, he can also experience the same thing if he were in a strong gravitational field. So remember that space is a fabric and it bends. It has curvature to it. So if we were to look at, say, a black hole, and somebody had a clock that was deep inside the black hole where there's a really strong gravitational field, and we had a second observer watching them in a not a strong gravitational field, they're going to experience two different time changes, or two different ticks. The person that's closer to the black hole sorry, let me back up. The person that's watching the person next to the black hole, they're going to see their time slow down. So the time for the person inside the black hole is going to slow down, which means they're not going to age as much. The person inside the black hole watching the people on the outside, if they can, they're going to see their time speed up, which means they will age faster. So not only does acceleration affect the amount of time to tick, a black hole can also affect the time it ticks. And the stronger the gravitational field, the slower the time, the more time slows down. This can be seen in the movie Interstellar, in which when Matthew McConaughey, spoiler alert, pause now if you don't want to hear this, when Matthew McConaughey comes back to Earth, or the new planet that the new Earth we can say, he's aged regularly from our perspective, but everybody else aged a lot faster because for him time slowed down when he was on the planets that had a strong gravitational pull. Whereas everybody else, from his perspective, everybody else time ticked faster. If we go back to the twin paradox, we can also measure the length contraction for the twin traveling in the spaceship. So the person on Earth, Al, said his twin traveled 7.5 light years down and 7.5 light years back for a total of 15 light years. What we can do is calculate what that distance felt like, or what that distance was for Joe on the spaceship. Sorry, I can't write and talk at the same time. Whatever. Contraction. So the proper length, that's what Al measured to be a total of 15 light years. And we want to find what was the contracted length for Joe. So we'll use our formula for length contraction. The contracted length is the proper length times the square root of 1 minus v squared over c squared. So we get 15 light years times the square root of 1 minus 0.5 c quantity squared all over c squared. Plug and chug, and we get a length to be about 13 light years. So we can see for Joe, he only traveled 13 light years when he's traveling at 0.5 times the speed of light. We said earlier that the speed of light is a constant value, which means that no matter how fast you're traveling, it's always going to be the same value, 3 times 10 to the 8th meters per second. And then the two consequences of that is that there has to be length contraction and time dilation. So if we look at our two answers, if we pretended that Joe was traveling at the speed of light, in this case his speed is 0.5 c, we could calculate his velocity to be distance over time, which is 13 light years all over 26 years, which gives us 0.5 times the speed of light. So these are two consequences of the fact that the speed of light remains the same no matter how fast something is traveling along with it. And that's it for this video. Thank you for watching, and I'll see you next time. See ya.